Hi, thanks for taking the time to watch this presentation. I'm going to tell you about some methods that we've been developing for using supervised learning to design optimal feedback controllers. This is joint work with my advisor Gong and our collaborator Kang. So we're interested in this standard optimal control problem, minimize the cost functional J with some dynamic constraints and over a fixed time horizon. There's broadly two ways to do this. The first is Pontryagin's principle. It's a 2.0D boundary value problem. Solve forward for the state X and backwards for the co-state lambda. This gives you the optimal control U star, which is open loop as a function of T. There's a lot of computational methods to do this, but unfortunately, they usually aren't like fast or reliable enough to use in real time. So ideally, we'd like the optimal control in state feedback form. And to do this, we need to solve the Hamilton-Jacobi-Bellman equation. This is a n+1 dimensional nonlinear PDE, and this gives you the value function, which is the optimal cost to go at any point t in x. Now, the optimal control then depends on the gradient of the value function. So ideally, we could solve this offline and then have the optimal control that way. But this is really hard, right? Solving high-dimensional PDEs is hard. So it's an active area of research, and today our approach will be to take the method of characteristics. This connects the Hamilton-Jacobi-Bellman equation with Pontryagin's principle along the characteristics of the value function. So you have correspondence between the open loop optimal control and closed loop optimal control, the value function, the optimal cost to go, and the gradient of the value function and the co-state. So what we'll do is generate a data set by solving boundary value problems associated with random initial conditions. This gives us inputs t and x and some associated outputs v and lambda, which are the value function and co-state. We'll use a neural network to try to represent the value function and train that neural network by reconstructing the output data for V. To improve learning, we try to apply our prior knowledge that the co-state should be equal to the value function gradient. So we take the gradient of the neural network using automatic differentiation and simultaneously learn that co-state. This really improves learning because we're making the maximum use of our data set by incorporating as much information as we can, and also applying some prior physical knowledge to get a better shape for that value function, not just learn point-wise fitting. So let's see how this works on an example. Here we have a 6-dimensional model of a rigid body satellite. This is a nonlinear equations. And we try to stabilize this by minimizing a quadratic cost function. So we'll pick parameters to match up with previous results using a sparse grid characteristics method, where instead of a neural network, they use interpolation on a sparse grid. So here are the results. On the top graph, you have the validation error of the neural network. And the bottom graph, you have the training time. And this all depends on the number of data points used for training. That's what you see in the x-axis. It also depends on mu, which is the weight on that gradient loss term. So a higher mu means more emphasis on learning that gradient versus just fitting the value function point by point. And you can see that with the right choice of weight there, you seriously improve your accuracy by an order of magnitude or more. And that lets you, with just 512 data points, beat a sparse grid characteristics method with 44,000 data points. So with that gradient term, we really improved data efficiency, and that's important because in high dimensions, a lot of the cost is actually in data generation. So we think that this is a potentially promising way to do this. Let's just finish by looking at a closed loop simulation. Here you have the neural network controlling the system. And we've implemented this with a zero order hold and some noisy observations to kind of make the problem a little bit more realistic. And you can see under these conditions, the neural network does a great job stabilizing the satellite. So here I've showed you just a taste of one possible way to use machine learning to do optimal control. We think this is a nice approach because it's grid-free, and we've been able to do it in up to 64 dimensions at least. And although neural networks can be difficult to train, all this difficulty is done offline. Real time, the computations are cheap, and we hope that this can make the method be useful for actual feedback applications. Finally, I want to emphasize that we're not just using machine learning for optimal control. Our knowledge of optimal control influences or informs the kind of machine learning we want to do. Right? For example, we don't want to throw out all this knowledge, we want to keep in, say that the gradient of the value function should be equal to the costate, and things like that can really improve our learning. Thanks for listening. Hope you enjoyed this talk, and if you are interested in further, please check out the references in the video description.